Hello everyone, welcome to the lecture today. We have been discussing so far a spring mass damper representation of different type of system. But as you would realize, in reality, most of the structure are not discrete mass spring and damper, right? So you have a structure like you have beam, you have column. So in order to get the response of this system, we need to have a method through which we can simplify a continuous system to a single degree of freedom system. Okay, so if you have a beam column, then how can we simplify that to a spring mass damper representation? And because we have already now in basically in discussions, we have already learned how to get the response of a single degree of freedom system, it's just mass spring damper, to different type of loading. We can then find out the response of a continuous system once it is reduced to a single degree of freedom system to different type of loads. And the way we simplify a continuous system to a single degree of freedom system is through a concept called shape function. Okay, and we are going to learn about that today, and we are going to see how we can employ the idea or the concept of shape function to convert single degree of freedom continuous system to a spring mass damper representation of a single degree of freedom system. So let us get started.
So, till now, what we have seen, we have considered a single degree of freedom representation of general structures. Okay, so it could be a spring mass damper representation. Okay, now most of the system in reality are not single degree of freedom system, and for many system, single degree of freedom system might not be an appropriate approximation to get the response or desired response quantities of interest. So what we typically would like to do, move from analysis of single degree of freedom system to multi degree of freedom system. Okay, now in order to do that, to make that transition, we're first going to learn what how do we analyze if we have a continuous system. For example, let me take the example of this cantilever beam here. Okay, now for this cantilever beam, depending upon how many points we consider on this cantilever beam, in general, a continuous system, okay, would have infinite degree of freedom. Okay, now it might be appropriate for some cases to consider or analyze this using a single degree of freedom system, or for more accurate representation, we might have to switch over to multi-degree of freedom system. Now, although multi-degree of freedom system supposed to be more accurate, however, it is also computationally expensive, as well as the standard solution might not always be available. Okay, but we have seen that for single degree of freedom system, okay, if we have this equation of motion, we have derived response for different type of excitation, and we have learned how to get the response using different type of numerical method. So we have standard results available for single degree of freedom system. Now the question comes, is there a way in which or using which I can analyze a continuous system without having to get into the complication of analysis associated with multi-degree of freedom system? And that's where the generalized SDUF system comes into play. Okay, so as I've said, if you look at any system, any continuous system, in general it would have infinite degree of freedom. So our goal is that somehow we can reduce this system to a single degree of freedom system and then find out K equivalent and M equivalent. So although I'm analyzing a continuous system, I would utilize some methods through which I can do this simplification so that I don't have to do the calculation for multi-degree of freedom system. Second thing, if you remember, till now what we have considered, movement of a single mass. So either mass was simply attached to a spring, okay, or it could have been a rigid bar that might be hanging, okay. So in both cases, I need only 1 degree of freedom system or 1 degree of freedom to represent its displaced position from its original equilibrium position. Okay, now in these cases, and let me take the example of this rigid bar here. If you look at this rigid bar, the rigid bar is constrained to move around this point. Okay, move around the point of rotation. Now, on this rigid bar, if you look at it, let us say we consider a displaced position in this fashion. Okay, now in this displaced position, depending upon where is the location of a point on this rigid bar, I can have different displacement. However, I would have the same angular velocity or angular acceleration. Okay, so two things come into play for a continuous system. One is displacement. Okay, so now we are talking about, or let us not call it displacement. Let's say the first thing that comes into picture is the location of a point. Okay, location of a point. And the second thing that is common to single degree of freedom system or continuous system is the time variation of the response. Okay, so we are going to consider the time variation of response. So while for a single degree of freedom system, we had considered only location of a single point. Now for a continuous system, there would be several points on the continuity of the body, and we'll have to basically find out the displacement history of each and every point on that body. Okay, so that's why the generalized STU of system comes into picture. So what do we do for a continuous system? We represent the deformation. Okay, so let us say I have a deformation which is function of now x, okay, and t. This represents the deformation of any point on a continuous system. So let me take the example of this cantilever beam here. Okay, and let us say under action of some force, okay, it is deforming so that in the displaced position, okay, this is how it looks like. Now this deformation is what we are talking about. This is our u of x, okay, this quantity here, where x is the distance from the fixed end, okay, or any reference coordinate system that you have assumed for that cantilever beam. So this is what I need to find out. Okay, and subject to, let us say there is a force Pt here. Okay, so subject to this force, I would like to find that out. So the first objective of this chapter is to find out this u of x and t, okay, subject to this excitation. And the way we do that is we decompose the deformation in terms of two functions. First is phi x, which is only function of the location or x, and the second is zt, which is the only function of time. Okay, and phi x basically is called shape function, okay, and zt is called generalized coordinate. Okay, and let us see what are the significance of these two quantities. Now if you look at the deformation at different instant for a continuous body, for example you have this cantilever beam here, okay, so at different instance of time it would be something like, let us say this is t1, then this is T2 here, and then so on. Now, two things are here. Considering that the body is vibrating, okay, there are two things that are happening. First, the movement of each and every point on the body with respect to time. Okay. However, if you look at it, let us say location of this point, which is at the farmost end, okay, compared to another point which is here. Okay, so these 2 points, and then after some another time, let us say the rotation location or the ratio of the vertical coordinate, these two are going to remain same. Okay, and this is the first thing that we need to, or we are going to talk about, is the shape function. So to look at into the shape function, first you need to think about what is shape. Okay, shape basically represents the relative aspect ratio. You can think it in terms of aspect ratio of any body. So for example, if you look at these two, these two might have a different size, but they have the same shape. And whether they have the same shape, it depends on the relative aspect ratio. Okay, so the aspect ratio of the sides of these two. So what happens similarly in terms of deformation, I'm going from t equal to t1 here to t equal to t2. So while my shape is changing, while my size is changing, my shape is still maintained. So if I can find out some function that can represent the shape of a structure and multiply this with some other function that represents the time variation, then that is going to give me the overall deformation. For example, in this case, if I represent the shape as a, let us call this as C and D. Okay, so let us say A by B is equal to C by D equal to some quantity. Let us say some aspect ratio is K. Okay, so if we can represent the total size as K times some time variation, all I need to do is find out this time variation, and if I multiply this with the shape of the body, it is going to give me the overall size. Now take that analogy and let us revert back to the vibration of this cantilever beam that we are considering. So let us say I'm able to represent, and since this is one-dimensional body in terms of coordinate x, let us say I'm somehow able to represent location of each and every point on this deformed shape of the cantilever beam through a function phi x, and then there is another coordinate zt which is basically changing with time. So if I multiply phi x with zt, it is going to give me the u of xt, which is basically the overall deformation at each and every point on this beam. Okay, now shape does not change with time, as you have observed here or here. What actually is changing is the generalized coordinate. So the time variation actually comes from the generalized coordinate zt. Okay, and our goal is somehow is to derive an equation which, let us say, maybe of this form here. Okay, so we have equation of motion. So our goal is to somehow, using this shape function, is to find out an equation something like this. Okay, if I'm able to find that out, I would be able to get zt as a function of t subject to the excitation p equivalent t. Okay, and once I get that, all I need to, so that would represent how the deformation actually is changing with respect to time. And if I multiply that with the shape of the structure, which represents the location of each and every point, the relative location, then I might be able to find out the overall deformation of each and every point of the body at any time instance t. And that is what we will try to do here. And let us try to understand this through two examples. First, I will give you an example of a rigid body. Okay, so if you consider a pendulum, okay, let us come back to the pendulum. Now, say at any time instant t equal to t0, the pendulum was in equilibrium position, and then at any time instant t equal to t1, it has come here. Now, if I consider x to be the coordinate represents the, say, in this direction, okay, and this to be the theta t, which is changing with respect to time, I can find out location of each and every point using this equation here. Let us say this is u of xt, the overall displacement, which would be equal to whatever the x is times theta t. Okay, so whatever theta t we are considering, we are going to multiply with that with x. Now for this case, and this we have already been doing, remember r theta basically represents the location on the, or the radial location or on the circumference of any particle. Now for this case, uxt represents the displaced position of any point. Okay, now if you consider here, basically the x is the phi or the shape function. Now this is a rigid pendulum, okay, and the mass is hanging at the end of it. So here x represents the shape function, which is a very simple function, and if I multiply this with theta t, which represents here the zt, the time variation, the multiplication of these two gives me the displaced position of each and every point on this body with respect to its original position. So for rigid, okay, for a rigid setup or rigid system, let us say rigid SDOF system, okay, I can easily find out the shape function, and that would be unique, okay, because there would be only one way in which the shape of the structure can be represented. However, if I compare that to, let us say, a beam which is, say, simply supported beam, let us take example of a simply supported beam. Now, as I said, if the system is considered to be a continuous system, okay, there would be, a continuous system has infinite degrees of freedom. So by definition, it would have infinite modes of vibration, and that you might recall from your knowledge of sound theory, okay, wave theory, where you consider different harmonics of vibration. It is somewhat similar to that one. So, and we will look into that more detail when we talk about the multiple degree of freedom system. Okay, so a system like this, the simply supported beam, a continuous system, it can vibrate like this, or another mode of vibration could be like this, or another mode of vibration could be something like this, and so on. Okay, and it can have, like, infinite degrees of, or infinite modes of vibration. Now the question becomes, if I have to find out phi x, which of these shape functions do I need to take, and how can I get those shape function or the mode shapes? Okay, now we are going to get into multiple degree of freedom system, where we are going to do the exact determination of the mode shape. However, for this chapter, we don't want to do that. We don't want to do all the analysis to get the exact mode of a system. What we are going to do though here is assume that the first mode of vibration is actually represents the deformed shape, and then assume any shape function or any function phi x that somewhat represents the deflected shape of the structure. Okay, for example, if I consider a cantilever beam, I know that in deformed position, it looks like something like this. Now, this can be represented by various type of expressions. So, if I consider this horizontal axis to be as x, okay, and this deformation to be uxt, okay, to represent the deflected shape, let me first write down uxt as phi x times zt. Now, the deflected shape can be represented in various ways. The deflected shape, I can either look at it and see, well, it represents a parabola. So, the deflected shape can be represented using the expression x square by L square. Okay. I can also look at it and see, well, it does look like a function. Okay, a cosine function, which is this much. Okay, so that at x equal to 0, it is 0. And at x equal to L, it is actually 1. Or this deflected shape can be approximated with the static deflected shape of a cantilever beam subject to the point load at its end, so that it can be represented using 3x square by L square minus x cube by L cube. Okay, so depending upon what shape function we choose, we can have multiple shape function to represent the deflected shape of this structure. Now, as I've told you, I'm not trying to determine the exact mode shape, which I could if I did the multi-degree of freedom analysis using large number of modes. But here, my goal is to do it without having to get into all the mode determination. So I'm going to assume the deflected shape to be one of these functions. Okay. Now these functions, as you can imagine, would provide you approximate results. Okay. And whether that approximation is good enough or not depend on the shape function that you have selected. Okay. Now all three shape function can be used to represent the shape of this deflected shape of this cantilever beam. However, the only condition that all these shape function must satisfy is that all selected shape function, okay, must satisfy the displacement boundary condition. And what is a displacement boundary condition? So, for example, this cantilever beam has 0 displacement at its left end as well as 0 rotation. Okay, so whatever shape function I select, that must satisfy that. Now, what we usually do, like in this case, when I write uxt equal to phi x times zt, okay, in these type of scenarios, we typically write phi x such that it becomes, or we normalize phi x with respect to a point of reference. Okay, for example, the actual deflected shape, okay, the actual deflected shape of a cantilever beam subject to a point load at its end, okay, let us say this point load is 1. So the deflected shape actually looks like something like this. Ux, or this, let us say here, Ux equal to 3L x square minus x cube divided by 6 EI. Okay, this is the actual deflected shape. However, when I will represent the deflection, okay, I'm going to write it as this deflection with respect to some convenient reference point. For example, I know that the deflection at the end is PL cube by 3EI, which for unit force becomes L cube by 3EI. So if I write my Ux as L cube by 3EI, okay, times, okay, so if I take that common, this becomes 3 by 2 x square divided by L square minus 1 by 2 x cube by L cube. Okay, so I can normalize such that this represents the shape function and this represents the z at any time instant. Okay, and zt would be this factor multiplied with something, so that my phi x is now normalized with respect to the deformation at the end of this cantilever beam. Okay, so usually whatever the shove function that I get, the deformation that I get, let us say delta x, and you divide it with respect to some reference point. Okay, so that let us say here it is L cube by 3I, such that when you substitute phi equal to L, it becomes 1 here. Okay, if we do that, then basically u of L becomes phi of L times z, which is equal to 1 times z. Okay, so if I normalize it, then my deformation becomes the generalized coordinate at that reference point. So I have done it with respect to the end deformation here. Okay, and you can choose it any convenient point. For example, if you have a simply supported beam, something like this here, you can normalize with respect to deformation at the center. Okay, and you can select a shape function so that it becomes, okay, at L by 2 it becomes 1. Okay, and it is up to you how to select that. Okay, so once that is known, okay, I need to first find out those shape function for different type of structure. All right, now let us get into how do I simplify. So I know that to represent the deformation of any point or at any location in a continuous system, this would be, the deformation would be represented as this. Now, once I have assumed the phi x, the question is how do I get the z of t? And to do that, we have mentioned that I need to simplify the single degree or the continuous system to a single degree of freedom system, okay, to a SDF system. Okay, and let us see how do we do that. So what we are going to do, we are going to consider an example of ground excitation, or let us say ground, let us call it seismic excitation. Okay, so basically what I'm saying here, I have the same cantilever beam. Okay, and it is undergoing vibration due to ground. Now due to this, it would have some vibrations, there is displacement due to ground, which is, let us say, is UGT, plus it would have its own deformation, the relative deformation, and it would be different at different location. Let us say this is coordinate x, and let us say at any time instant the deformation is actually u here. Okay, so this represents the deformation of a structure. Now to get the equation of motion, okay, so we need to get the equation of motion here. Let me fix this. So to get the equation of motion, okay, I know that the total acceleration at any location in this structure can be represented as ut of xt would be equal to ground acceleration plus the relative acceleration of that point. Okay, now knowing that, let us first find out what is the inertial force due to this acceleration. We know that inertial force at any point in this can be, so inertial force would look like something like this. Okay, I'm applying it opposite to the direction of motion. So at any height x, inertial force I can write as Fm Fi of x and t, and this would be mass times acceleration. Let us say the mass is a function of x. Okay, so it doesn't have to be a constant mass. So the mass density is actually m of x times the acceleration, which I have just written as m of x, this ut of x and t, and this can be written as mx times ug of t plus ux of t. Now this is effectively the external force that is acting on this cantilever beam. Okay, to get the equation of motion, what we are going to do, we are going to use a method called principle of virtual displacement, and you might have already come across this in different courses. Okay, so we are going to utilize principle of virtual displacement. Okay, now principle of virtual displacement basically says if a system is in equilibrium and if you apply a small virtual displacement, let us say del u of x, then work done due to this virtual displacement, okay, due to this virtual displacement, work done by the external forces are equal to work done by internal forces. Okay, so let me repeat it again. If a system is under equilibrium given a small virtual displacement, then work done on the system due to this virtual displacement and due to external forces is equal to work done by internal forces, okay, due to this virtual displacement. So the external forces, as I have mentioned, is this inertial force here. Okay, now work done due to this, let us write down WE. It would be, so what I'm going to do here, I'm going to write TWE and internal forces. Now external force, as you know, can be computed as force times displacement. Okay, so let us say this is the deformed position and it is given a small virtual displacement, which is again a function of x. So this is small virtual displacement, which is del u of xt, the function of x and t, and at the top it was, let us say it was z. Okay, because I'm normalizing it with respect to the displacement at the top, and let us say this is del z. Okay, all right, so let us see due to that how much is the work done. So work done due to the inertial forces would be Fixt. Okay, this is force at any height x, and if you consider the force over the height dx, it would be this times dx. So this is the total force over the height dx. Now this is undergoing a virtual displacement of del uxt. Okay, and I need to integrate it over the whole height to get the total virtual work done by the external forces. Now for the internal forces, if it's a flexure system and I'm assuming that there is no significant shear deformation, okay, the work done due to flexure, you might already know this, is done by the internal moment mxt okay, due to curvature del kx. And I know if u is my deformation, then u dash x represents the angle and u double dash x represents the curvature. Okay, so the internal work done would be work done by this moment mxt times theta, or let us say it is del theta. Okay, and this need to be integrated over the whole height. Now del theta is nothing but curvature times the height that is being considered. So I can write this as 0 to L mxt times del kx times dx here. Okay, and you might remember from your undergraduate classes from beam theory, mxt is basically written as eix times u double dash x. Okay, and then there is del kx times dx. Now before going further, okay, let me point out that if I consider my ux to be phi x times zt, then u dash double dash x would be phi double dash x times zt, and u double dot t would be phi x times z double dot t. Further, because ux is this much, my del ux should follow the same shape function, and it will become del ux by phi x times dz, and also del u double dash x would be phi double dash x times del z. So we are going to utilize this and substitute in these two expressions here and here, and let us see what do we get. So this expression is nothing but, okay, I'll have a negative sign mx times ugt plus u of x t double dot times dx. Okay, this is the external force, the work done by the external force here. Okay, and of course there is this term here del u of x. Okay, now if I simplify it further, I can take this ug double dot out and then substitute these expressions here so that I can get this simplified expression as the external force. Basically it would become minus ug double dot t mx and then del ux dx, okay, integrated over of course 0 to L, and then minus mx, and then substitute the expression for this, which would be phi x times z double dot t times del ux, which would again be del z here. Okay, so I have to include the del z term, or let me just first write it as del u of x times dx. Okay, and then what I can do, I can take out, or del ux I can write it as this, okay, and then take out del z outside. Okay, so that I get this as del z times minus ug double dot t 0 to L mx phi of x, okay, times dx, and then here minus z dot double t and then 0 L mx phi x square dx. Okay. Similarly, I'm going to further expand this term here. Okay, this here, substitute it so that I can write it as e of ix times phi double dash x times zt times the curvature is nothing but del of, okay, so it would become phi double dash x times del z times dx. So this is eix times phi double dash x, okay, and this whole times del z. So if I equate these two equations, expression, and then bring it to right side, okay, the expression that I get is del z here times mx times phi x square dx, and this whole times z double dot t, okay, plus I have this term here. This term that I'm going to write next is 0 to L eix, okay, phi double dot dash x square dx times z of t, okay, plus this term here, which is 0 to L mx phi x dx, and this whole term times ug double dot t, and this is equal to 0. Now I know that my virtual displacement del z cannot be equal to 0 because I have assumed it to be a finite virtual non-zero displacement. So what I'm left with, the expression inside the bracket to be equal to 0. Okay, so let me do that. Okay, let me now have a look at carefully these terms that are inside this bracket. These terms only depend on the parameter x or the location, and it is not a function of time. Okay, so if I consider this expression, okay, let me write this as m equivalent times z dot t plus another constant parameter, which is k equivalent times zt plus l equivalent times ug of t. And this is somewhat familiar to you from the expression of a single degree of freedom system, okay, where I have a second order differential equation in z, okay, the generalized coordinate z, and that is what I need to solve, okay, where m equivalent for this system is this expression here, okay, and the k equivalent is eix times phi double dot dash x, okay, and then I also have l equivalent, which is 0 to L mx phi x dx. Okay, so I have been utilizing the shape function phi x, okay, I have been able to reduce a continuous system to a single degree of freedom system, and then my job becomes very easy because I can solve this system and I can find out what is z of t. Once I find out z of t, which is the time variation of the response, I can multiply with phi of x, okay, as I have told numerous times before, to get my u of x of t. So the displacement of each and every point on that continuous system as a function of time. Okay, and that is how we solve any type of continuous system. We assume a shape function. Utilizing that shape function, we find out what is the m equivalent, k equivalent, and l equivalent. And then once that is found out, we solve this second order differential equation to get the value of z of t. Okay, So this is the procedure that we would be following to solve a continuous system. Now, you note one thing here, we have not considered damping. Okay. And as I have previously mentioned, damping, the C equivalent, there is no term such as like C equivalent that I can find out just from the properties, the geometrical and mechanical properties of the structure. Okay. So what do we do? Because damping is a very complicated mechanism. So typically we find out damping ratio from experiment for different type of structure and then use that to solve the system or include the damping in the system. Okay, so first let us write down this expression here that we have, okay, in this form. So let me rearrange that so that I can write it as, first for the undamped system, okay, K equivalent divided by M equivalent Z of T. This is L equivalent M equivalent, okay, times UG of T. Okay, so we can write this as Zt plus omega n square of Zt, and thus it is equal to, I'm going to define it as another parameter, Ug of T. Okay, now if I have a damping in the system, okay, you might know the familiar expression. I can further write, include the damping as zeta omega n times Z dot T plus omega n square times Z of T minus zeta equivalent G of T. So this is for undamped system. And if I know the value of damping experimentally, or let us say assuming some some ratio, I can formulate this equation like this. Okay, and this gamma equivalent is nothing but L equivalent divided by M equivalent, which if you like to write in terms of expression in phi x and mx, it would be 0L, okay, and here it would be mx phi x square dx. Okay, so we have been able to reduce our continuous system to a single degree of freedom system, okay, and find out, and utilizing that we are going to find out the response of the system. Now once we find out M equivalent and K equivalent, it is very easy to find out the frequency of the system as before. Okay, so the frequency square would be K equivalent divided by M equivalent, which is 0 to L EIX times phi x square dx divided by 0 to L mx phi x square x times dx. Okay, and then that would give me the frequency and subsequently the time period of the system. Okay, so this is how we reduce a continuous system to a single degree of freedom system. Now the next step is, given this, how do we get the response of the system? Okay, or before going into that, let us first see some example. For example, typically we said that if we have, let us say, a cantilever beam, something like this, okay, and a load is being applied, let us say at one end, we used to simplify this system to a spring mass system, saying that I'm going to assume my K equivalent to be 3 EI by L cube and then mass to be represented by tributary. But many times it won't be as simple as that, and I don't know what is my M equivalent here, what is my K equivalent here. Okay, and this method that we have just described is going to assist us in finding out this K equivalent and M equivalent. And how accurate it would be, it depends, as I said previously, on the shape function. Okay, so here what we are going to do now, we are going to consider this cantilever beam and then consider three shape functions. Okay, the first shape function would be basically phi 1 x, which represents the static deflected shape of the cantilever beam subject to a point load at one of its ends. So let us write down the first shape function as 3 by 2 x square by L square minus half x cube by L cube. The second is another shape function, which is 1 minus cos pi x by 2L. And then there is a third shape function, okay, which I'm going to write as the parabolic function x square by L square. Now, if you look at all these shape functions, all of these shape functions satisfy the displacement boundary condition for this cantilever beam, which is phi 1 equal to phi of 0 equal to 0 and phi dash of 0 equal to 0. Okay, so all I need to do is substitute this shape function in the equations that we have derived for mass and stiffness here to get the expression or to get the value of m equivalent and then k equivalent and then omega n, and compare to see using different shape function how do they actually affect the equivalent properties and the modal properties of this cantilever beam. Okay, so the job is simple, basically substituting this phi 1x, phi 2x, phi 3x in that expression for m equivalent and k equivalent and finding out the equivalent mass and equivalent stiffness. So for the first case, when we do, this value comes out to be approximately as 0.23 times ml, where m is the mass per unit length and L is the total length, such that the total mass is m times L. Okay, the K equivalent, you would find out that it comes out to be equal as 3 EI by L cube. Okay, and the omega n that comes out to be is actually equal to, okay, you can simply substitute the values and then you can find out what is the value of omega n for this case. Okay, for this case here, it would simply be 3.57 divided by L square. Okay, and this would be EI by mass per unit length. Okay, now for the second case, when you substitute that, you will see this value comes out to be around 0.227 ml, and this value comes out to be around 3.04 EI by L cube, and omega m comes out to be 3.66 EI by m, and this is L square. Okay, for the third case, if I do that, okay, find out this comes out to be 0.2 times ml, this comes out to be 4 EI by L cube, and this comes out to be around 4.47 divided by L square EI by m. Now if you look at that, we see that the mass that is participating in the dynamic response is actually not m by 2. Remember, ml is equal to the total mass. So it is not actually m by 2, but it is actually 0.23 times, or approximately 1/4 of the mass. Okay, which makes sense because the mass which are further away from the fixed support is going to participate more compared to the mass which are closer. Okay, and that's why the effective mass that actually participate is 0.23 times the total mass. Okay, and the K equivalent that we get is actually 3 EI by L cube, which is expected because we had assumed the static deflected shape to be the shape function in this case, and for the static deflected shape, the equivalent stiffness, okay, is actually 3I by L cube. Okay, for the second case, this is again, okay, any arbitrary function to represent the deflected shape. Okay, so when I use this, I look at here, again, the mass is around 0.23, the stiffness is 3.04, which is again close to the first shape function, and the frequency is again 3.66 times that same common factor. So first and the second shape function produce results which are quite comparable. Okay. However, if you look at the third one, there are not significant, but like, I mean, you can look, there are like, differences which are much more than the first and the second one. So you have 20% of the total mass. However, the stiffness now increases to 4 times EI by L cube. And even your frequency is 4.47. So the question comes, how do I know which shape function is appropriate? So typically, a static deflected shape of any structure can be assumed to represent the dynamic deflected shape, although it won't be exactly equal. However, I know that a static deflected shape would always, because it constrained by the same boundary condition, it will represent the, or it will satisfy the displacement boundary condition. Okay, and then we can check. Now in this case, what I see here, all three satisfy the displacement boundary condition. However, only the first to satisfy the force boundary condition. Okay, and I'll show you how. Now, the force boundary condition here is that I know a cantilever beam at the fray end, the moment should be equal to 0. So, the moment at length L should be equal to 0, which means this expression EIX times phi double dash X, okay, times Z at X equal to L should be equal to 0. Now, if I look at it, phi 1, not here, at L is actually equal to 0, phi 2 dash actually equal to 0. However, phi 3 dash double dash is actually equal to 2 by L square. So it is not equal to 0. So while all three satisfy the displacement boundary condition, the first two also satisfy the force boundary condition. So it represents the deflected shape, okay, that also satisfy the additional force boundary condition. It is more likely to represent the dynamic deflected shape compared to the third one, and that's why third one produces large deviation compared to the first and second one. Okay, so this is how we select the shape function. Okay, and shape function is very critical to the accuracy. As long as satisfy the displacement boundary condition, usually the results are reasonable. Okay, but if it also satisfy the force boundary condition, your results would be very close to the actual solution. Okay, so with that, we would like to conclude our lecture today, and in the next lecture we are going to further study how to apply this to get the response of a continuous system in terms of internal forces and moment. Okay, thank you.